Okay, so I forgot, of course, to connect Q and Q. So we have capacity, but we don't use it. It should be here, but I will write it down. So we have that. Now, usually you should be something absolute, but you can be temperature, and temperature is notoriously used in terms of non-absolute coordinates like Celsius. Kelvin is an absolute coordinate, but Celsius. So the problem is that you cannot multiply Celsius. So it's nonsense to say times 5 degrees Celsius or 2 times 5 degrees. So it's nonsense to say times 5 degrees Celsius or 2 times 5 degrees Fahrenheit. It doesn't make any sense. So that's why usually in the literature they say that dq dt is so this is pi of star 0 du dt. They take the derivative. If we don't, if you are in absolute scale, we can write directly q is p times star 0 of u. Or also, it depends on the maybe on the model that star 3 of dq dt, star this, sorry, of dq dt is e tilde of du dt. And so, I don't know how this code. I think I read relation between amount and potential. Okay, and this should be here. It doesn't matter the other, but it should be before the boundary conditions and the initial condition. Okay. Now I'm going to write the CNC formulation. I will save a bit of time and just change something. So, and to wait for you to write it down. So we have the CNC formulation. And this is, so the time now is, again, it's continuous. So we have continuous time and discrete space. And K mu is an oriented, it's a finite oriented Riemannian D-mesh for this image. This integer, and this is space is continuous, space is discrete. We don't discretize time because we don't know what, I mean, don't see a point because time is very regular, it's one-dimensional. It may have some internal structure, right? Maybe there is natural time intervals that are different. So, for example, we go from 0 to 1.2, 0.1, but then to 0.3. But we can discretize it later. Now, because we're K, we are making K into two boundaries. And then so it's in decomposed into Neumann-Dirichlet boundary. V now lives in D minus 1 cells. And F lives in D cells. GD is 0 cochain on the boundary, on the Dirichlet boundary. And let me write this more properly. This is from I to CD minus 1 of gamma n. And U0 is in C0 of K. Yeah, I hope you put some place on your notebook and write this out later, because I want to go next. So this is again infinitely, because the interval smooth functions, but here it takes a cochain, and usually it's diagonal. So if we take a basis cochain, the result will be basis cochain on the same place, but with different coefficients. So we have conductivities. Now the conductivities are they are not interchangeable, because on a discrete mesh these two spaces are not isomorphic. So we have to be careful at the beginning what we choose. Why is this kappa different? And this is C0K, C0K. Okay, let's write this down. So K and K kappa kappa tilde and P tilde are not interchangeable. Changeable on a mesh, since hot stars are not invertible. So when we model, we have to choose which to compute. There is some discussion in the new version of the preprint where we discuss how these terms are calculated. If the material is isotropic and the coefficients are the same everywhere, they're just constants and doesn't matter if it's tilde or not. So this is the setup, the known variables and the unknown quantities. So this is the strength of this method, that of the continuous smooth textile calculus formulation, that the discrete one just is directly direct translation. We just change every discrete the continuous space and operator with discrete analog. So here Q is a deform. And now this, if we assume, for example, some 3D mesh, this will be a tree form. What does this mean? Well, the amount at every volume we split to have some microstructure, and every volume has some energy at any point. Unlike in the continuum, when the volumes are some kind of virtual, here they're quite quite physical. So it has obvious physical meaning. The flow rate, again, it says how much we have some surfaces, and we measure how much it flows, the flow rate through each surface. This is a physical surface of the microstructure. The temperature is some potential. It's not clear what is temperature. It's at points which on the original, because we work with Forman, usually with Forman subdivisions, on a original mesh, the temperature, the potential is given for any cell of the initial complex. So because points in the mesh K correspond to all cells on the original mesh M. This is different M, and we have temperature, for example, given should be calculated at each element. And the governing laws, here we change this to this. Here we change this to delta star, and this is the same, 0. Here we change wedge product with cup product. The traces are the same. Okay, maybe I should put that these are okay. This is okay. Maybe here as well. If you even if you don't put it, this doesn't matter. It's a different model, so I just want to make it different from the continuous one. And here again. Okay. I'll wait for it for a bit for you to write it down. So the model is exactly the same. Everything is translated literally. You copied it? Unfortunately, you cannot apply copy paste on a notebook.
Easy for me.
Yeah. Can I erase this part of the board here? Maybe, okay, maybe you can put case here, but doesn't matter. If you only work with the discrete one, you don't need to distinguish between continuous and discrete. So this is just for, because I will do them in parallel. So um, okay. So so now we will derive in parallel wave formulations. But for exterior calculus and for the EC and CMC model, the EC and CMC models. So we have the setup, and so we will do calculations on EC and transport the result, translate the resulting formulations to CMC. And we'll do only transient, so we will do only transient. Steady state one formulations. Are derived when d of something dt is what's called is removed, is ignored, and all known and unknowns, known and unknown variables, quantities are set to be time independent. Okay. So for example, here these equations will be the same. This will be ignored. This will be 0. And we won't have initial condition. And initial condition is ignored. is ignored. Okay, maybe without brackets and initial cognition is ignored. Okay. Now let's do Primal week. What's the okay on Monday? I did something like primal strong formulation, and our first article was with primal strong formulation, not exactly like this, but equivalent. Unfortunately, it's problematic how to apply Neumann boundary conditions, and because in the primal formulation, the unknown is usually temperature, the potential, but it's not clear because this condition naturally lives on surfaces, and the unknown is on nodes, and it's not very clear how to fix that. In a paper with Chan how we suggest something, but I think we usually work with zero Neumann. But in general, we can have non-zero Neumann with weak formulations. So let's start with the primal weak. Okay, everyone has written this. Yeah, so this field, I will remove this here. But leave the governing clause and remove this here. So let's start first with the primal weak formulation. Oh, as I said, we will start in exterior calculus. I will look at the notes in order not to mess something. So let because usually we use V, but because V is already used, take down W. V is this is time independent. So this is a function in the kernel of trace gamma D, which is the set of all functions omega, such that trace of omega is W. This is W, it's not omega. Is 0, which is the same as the space of functions from M to R, such that W with respect to the Neumann, the Dirichlet boundary is 0. Okay. Now let's calculate this term here. Integral, then integral of M of omega and d minus 1 q, we'll see why we use this term, is the following. This is so this is we can interchange because this is 0-dimensional. This is integral over M of d minus 1 q, which double W, and here we use trick code integration by parts. We write this as integral over M of d of Q wedge W. So this is minus 1 to the power of d minus 1, I think. Q wedge d from d W. Something is off here. D. Okay.
First is d minus 1, the second is d0. The first differential is d minus 1, and the second is
This is d0. Okay.
0, and the first one is d minus 1.
Yeah, but I shouldn't have this thing here. Okay, it's fine. It's fine. We will fix this. D minus 1, okay. And this is now, this is the first, the trace of Q and omega on gamma out of dm. This is Stokes theorem. And the second, we will swap the terms. So we have minus 1 to the d minus 1 integral of m. But then when we swap, we have minus 1 to the power of d minus 1 d0 w wedge q. Because this is one form, this is d minus 1 form, and we have graded commutativity property. Now this is this will be integral over gamma d trace gamma d q with trace gamma d omega plus integral of gamma n trace gamma n q with trace gamma n w, and this will be just, these are cancelled. This will be integral over m d0 w wedge q. Okay, now this is 0. You see, this is 0. So this is integral of gamma d trace gamma d with 0 plus integral of gamma n, and this is gn with trace gamma n of w and minus integral over m and d0 omega wedge q. And so the whole is just integral of gamma n gn times, I think I can write it in the other direction. Yeah, I can swap this. So this will be trace gamma n w with times gn. Because this is a 0 form and multiplication and exterior product are the same, and this is d0 w with q. So this is integration by parts. Why do we use this integration by parts? Well, if you rewrite the, we can rewrite the continuity equation. So therefore, so multiplying continuity equation with W and integrating gives I could, but I'll do this now. Gives that integral of m of dq dt wedge w is integral of minus integral of m d minus 1 q wedge plus integral m f with w. Let's say this one here. So we integrate this equation. Of course, this is the discrete one, but in the continuous we have the exterior derivative, not the co-boundary apparently. And so this means that that's why we calculated this here. So this will become this with sign plus. So this will be integral over m d0 omega with q minus integral over here the plus becomes a minus gamma m trace of w with gn plus integral over m of f with w. WF. And now we can express Q as sum of QA, QD and use the, so this is integral over M d0 omega, which, so we'll have some minus sign for the diffusive part, be star 1 kappa tilde d0 of u. We will have plus sign for the advective term. So is the life okay? Okay. Advective term will be star dq with w, but star d, so this will be star integral over m d0 omega w, which with star d, and then q is p tilde of u, p tilde of u. No, we don't need star d here, only p tilde. Now in the discrete case, it may be not that clear, but they're not interchangeable, but in the continuum it's okay. So we have p tilde u wedge with v. This is the advective term. And then we have minus the trace, the boundary term, plus wf. wf. Okay. So, yes. Now in integral of m, since we also have integral of m of d0 w, which with star 1 tilde d0 of u is by one of the properties is the Hodge star of the inner product of star d0 w with this is star 1 with star 1 of kappa tilde d0 u. This is the d minus 1 product. And this equals to, we can remove the Hodge stars in the continuous world. On 1. Okay, I will know that, so note that star sigma star rho equals to sigma rho is not true for meshes on meshes in the discrete case. But it may be a good approximation, but it is an approximation we use in calculations. In not calculation, modeling, in simulations, Okay. And therefore, we get that the Q dt, which W is minus star this thing here, d0 omega kappa tilde d0 u plus the advective term plus d0 omega w tilde u v minus the boundary term plus integral m wf. And now we'll write this as follows. So define the following. Define A D W U to be D0 W kappa tilde D0 U. This is the diffusive part, this is the advective. And then, okay, I have this matrix here. This doesn't occur in the steady state, but W equal of U. Oh yeah, so this can be, this is P tilde of U. No. Let it be Q, let it be Q. For now. Oh yeah, why does? Because integral of dq dt with omega is, why is this defined that way? This is the inner product of star dq dt with omega, and this is star, this is p tilde of u with du dt. And this is approximately equal to d dt of p tilde u w, which is d dt of d w u. That's how I use this term. I didn't motivate it, but these are components of the previous calculation, and this is the first term. We have GW is integral of gamma m trace gamma n w with Gn, and Fw is integral over m of omega times f. Okay, let's write the wedge here. Yeah, I should have written the wedge everywhere because it appears in the discrete case. So yeah. And so then we get the following problem. So we get the following. B. Okay, here is written du dt, so we don't need the approximation. B du dt plus A d w u minus A advective w u is f of w minus g of w. This is a restatement of the previous calculation. This calculation here, maybe if I write this one, this is one prime. We have 5 terms here and 5 terms there. And here, this is true for any w in the trace, the kernel of the trace. Any w that is 0 on the Dirichlet boundary. So, like in standard finite elements, the Neumann condition is here. This is Neumann. So it is not a separate condition, but it is part of the equation. Hey, this is Neumann as well. Trace of gamma d 0 of u is gd. This is Dirichlet. and u of t0 is u0. This is initial. So this is the continuous one, and the discrete formulation so the CMC is a direct translation. So this will be exactly the same, but the operators, this will be inner product discrete one. This will be cup product, not wedge product. So discrete token EC operators go to CMC operators. It's written in fluid article, so you can check that. And now this formulation, especially when this is 0, when we don't have advection, has a symmetric matrix, positive definite symmetric matrix, this matrix here, and it's very easy to solve. Not easy, but how to say, well behaved, and we don't have problem with the Neumann boundary condition. It's like a standard finite element. Shall I do the mixed? Nobody's trying to. Okay, maybe who has some arrangements can go, but I will write the mixed as well. It will take maybe 15 minutes. Okay, I'm going to erase the primal. We can do the discrete. Okay. Now the mixed, especially is important in elasticity for nearly incompressible materials, I think. In the discrete world, it can be beneficial. So in the, oh yeah, we have the post-processing, I forgot. So post-processing. That Q is at least inside, so in the interior. On the boundary, it depends, but it's not that important. In the interior, Q is star 1 of D0 of U once U is found, a cup. Once U is found. This is post-processing. Usually incurs errors, can incur errors, can lead to errors. So if we tested the flow, we don't get the flow as a primal variable. And in the mixed formulation, the flow is a primal variable. So mixed with formulation. Here, Q and U tilde, which is the star 0 of U, are primal variables. Let's say primal variables. So they're part of the formulation. They're they are found directly, not by post-processing, but directly. So they don't get any errors in them. So here we define the following. We define R. So before W was 0 on the Dirichlet boundary, now R is 0 on the Neumann boundary. So let R be in the kernel of trace gamma D gamma n d minus 1. So this is the space of O d minus 1 forms on the boundary such that trace of S is 0. And right now we write S. Yes, I mean, because we fix R now, I just bounce a different variable. So write the constitutive equation as, so this is the constitutive equation, but with this type, kappa minus 1 qt is delta d star of star 0 of u, but this is the same as minus star 1 of d0 of u. And now, then we have the following. Then we do the following calculation. We take this inner product, and this is minus r star 1 d0 of u, just using this definition. And but by definition, if we can interchange the places, so this is star minus star 1 du r, and this is minus the integral over m of d0 u wedge with r. This is from the property of the Hochstar. And now again, we use integration by parts. So this is minus integral over m of u d u with r minus u wedge dr. This is integration by parts. And the first term is integration over the boundary minus integration. So this is the trace. Trace of u with r minus integral over m of u wedge dr. Now the first term is, again, split the boundary into Dirichlet and Neumann. So this is integral over gamma d trace. The trace is the trace of u wedge r is the trace of u wedge trace of r. This is property of the pullback, and this is trace of gamma d u with trace of r. This is property of the pullback, and this is trace of gamma d u with trace gamma d r plus integral over, so this is here, integral over gamma n trace gamma n u with trace gamma n r minus integral over m of u dr, which dr. Okay, this is 0 because, so this is 0 and this is gamma d. So the whole thing becomes integral over gd of gamma d wedge trace of gamma d of r minus integral over m of u wedge dr. Okay. But also kappa minus 1 q d with r, so r kappa minus 1 q is okay, so I add like this. This is r kappa minus 1 q minus, no, let this. So this is kappa d plus kappa minus 1 qa. The first term is this expression here. So this is, I forgot something or not? Not. This is integral of gamma d trace gd with the trace of r. This is n minus 1. Minus integral of m u h r. So this is the first term. And then the second is r kappa minus 1. And then we have star d of t of tilde, u tilde, wedge with v. This is d minus 1 and this is d minus 1. So this is the advective term. I just replace it. So maybe put some brackets here. Okay. Now let w tilde is another test function, but without any conditions for it. Then the continuity equation gives p du tilde dt w this is D, is F W tilde minus D minus 1 Q W tilde. Is this right? Yes, I think so. So we'll have everything. To finish. So define ARS to be R kappa minus 1 S. Here R and S are deforms. B diffusive is DD minus 1 R omega W tilde. This is integration on inner product on B cells. So here R is omega D minus 1 and W tilde is omega Dn. This is a dual temperature in some sense. BA, this term. This is R kappa minus 1 star D of P W wedge with V. This is D minus 1. Again, the same variables. C is this here. So this is C of is P U tilde W U tilde. This is so U tilde and W tilde are D forms. GR is integration over D of trace gamma D. So this is GD wedge with trace gamma D. D minus 1 R. R is D minus 1 form. Okay. Okay. And so we get the following, the mixed system. A RQ minus B transposed D of RU tilde minus B A G of RU tilde is minus G of R for all R in the trace of gamma n. This equation, I deleted it maybe. No, this is this equation here. So
The C one is that equation. Yeah. C. Yeah, this one. Over here is
is this?
Yeah, but over there is partial U tilde.
Yeah, because I will take a derivative. And the second is minus B T B D of omega tilde of q minus c of the derivative of u, so du dt, is minus f of w for any w in omega dm. And we have the boundary conditions. So the trace of. Now we have two main equations, not one. This is why it's called mixed system, because we have two equations. The boundary conditions, they are dealt easily, but so this is Neumann. And this is Dirichlet. This is Dirichlet. So in the primal case, Neumann is inside the equation and Dirichlet is imposed on the boundary. And here is the opposite. Neumann is inside, is a constraint, but the Dirichlet is given, is computed inside the equation. And we have the initial condition. So u tilde of t0 is star 0 of u initial. They're both initial. And q of t0 is kappa dd star 0 u plus p of w, p of u plus p of w, p of u which v. These are initial. So this is the mixed system. This is diffusive. This is QD. And this is of T0. And this is QA of T0. And here we are more or less finished. Just some final words of final words. The discrete system. So discrete system again. Is literal translation. And post-processing is at least in the interior. In the interior, U is star D of U tilde. Okay. And this system is very nice when this term is 0. It's not 0, I'm not sure what to do, but I haven't coded it. I coded it when this is 0. Okay. That's the end. I'm very over time. I want to do an example on a non-flat mesh. I have a let me see. Because I did one manufactured solution on a flat mesh, flat space, but it can be done on non-flat space as well. Okay, you can look at it in the page. It's in the 6th section, so thank you very much for taking this course. And are there any questions about this? This is heavy, a lot of computations, but not that hard. I mean, if you read them, they're not that hard. Okay, any questions? I think this is it.